Good evening, everyone. Today we will start with spectrofluorimeter and phosphorescence spectrometer. Okay, so we will be basically discussing about two instruments, but both of these instruments they are related instruments. The first one is the spectrofluorimeter. Okay, spectro we have already seen that it is associated with the term spectrum. Okay. Spectrum of what? Spectrum of electromagnetic radiation. Fluori, it comes from the word fluorescence. Okay, what is fluorescence? Fluorescence is a terminology where we see that some object or some material, object would be a wrong term, some material which can absorb light and so absorb light at a specific wavelength. So lambda A is the specific wavelength where it absorbs the light at which at which wavelength it absorbs the light, and it emits a light at a specific wavelength B. So even we call it a specific wavelength B or A, they are also basically a band of wavelengths. Okay. Lambda is also a band of wavelengths. However, the maximum absorption is at lambda A. So these are maximum values. Lambda B, it is also a maximum value. However, what I said that at lambda A, it is absorbing some electromagnetic radiations and it is emitting another radiation at lambda B. Now, under this condition, this lambda B should be greater than the lambda A. Okay. And we all know that wavelength is inversely proportional to the frequency. So F is inversely proportional to the lambda, and frequency is also directly related to the energy content of the electromagnetic radiation, right? So this means the energy content of A, it is greater than energy content of B. Okay. Now what is happening? Basically, if you consider this material, you are seeing that some light it is falling on and it is having an energy A, and it is absorbing some energy over here, and it is radiating another type of radiation which is having energy B, and this energy B is having a lower amount of energy as compared to the energy A. Now the thing is that you can look into the stuff uh, in a manner that, see, I am delivering you a lecture. Okay, suppose I'm giving you the lecture at a specific wavelength, say lambda A. Okay. So it is having energy A. Yeah. So over here you are having this lambda A. So I am having this lambda. Okay. Now what is happening? You are learning the stuff, and then what you are doing when I am asking you to represent the my lectures in the exam, So what happens? There are some people who are performing relatively badly. There are some people who are getting ES grade. So some people they are getting very high marks, and again there are some people average marks. Sorry, over here you are getting the average marks, and then you are having some people who are doing very good in studies. So you are getting a band. Okay. So over here you can consider this as lambda b. Now this lambda b, it is at a higher wavelength. Okay. So what is happening over here basically? If you see the information content given by me, is much higher than the information content given by you guys, and hence, and there are only few students who are able to perform very good, and they are just replicating what I will be teaching, right? So if you see the information content which is being given by me is higher than the information content given by you guys. Okay. Now when I am talking that I am teaching over here, I am giving you a particular instance where I am teaching, but I am a subcategory of teachers. You will find that there are some teachers who are teaching better than me. There are many teachers who are teaching on an average scale, which is at a lambda a value, and there are some teachers who are teaching excellently. Okay, so some teachers they are teaching very good, some averagely, and some very excellently. Okay, so in this case, if you see, there is a band, wavelength band. So this wavelength band, it is nothing but it is called excitation. Because you are exciting this material with this frequency of light. Okay, and consequently you are getting another frequency of band, and this band it is called emission band, which happens at a higher wavelength. But the thing is that you need to remember that the information what the teacher is giving, it is having more information, and the information what the students are usually reproducing in their copies, it is having lesser amount of information, and this information it is basically associated with the energy. So if you see, if a signal it is giving higher information, then it is called that the signal is having higher entropy, or in other terms energy, and if a signal is having lower information content, then they are said to have lower entropy and lower energy. Okay, so am I clear? Am I clear?
Yes, sir.
Okay, good. So fluorescence means it is a phenomena where the material or the matter it will absorb some light, and then it will emit another light which will be having higher wavelength, in other terms lower energy. And meter is associated with some device for measurement. So spectrofluorimeter is basically a device which helps you in measuring the spectrum of the fluorescence. Okay, literally this is the meaning of spectrofluorimeter. Then coming to the next one, phosphorescence spectrometer. In phosphorescence spectrometer, what happens is that here also there is an excitation band and emission band. Okay, which is similar to the fluorescence. Now, what is the difference? In the fluorescence, if you look into the timing of excitation, time of excitation and time of emission, it is in the picoseconds to nanoseconds range. Okay, that means this is a very this emission, it is happening very fast. Within a fraction of a second you will be finding that the light is being emitted, whereas in the phosphorescence this time it is greater than 10 to the power minus 4 second. To it may again go up to some days. So you may excite now, after say several days you may get the phosphorescence. Okay, it may so happen. So this is the basic difference between the fluorescence and the phosphorescence. And any spectrometer which is allowing us to capture the process of phosphorescence, it is called phosphorescence spectrometer. Okay. Now, as I told you, fluorescence. What is fluorescence? It is nothing but re-emission of radiant energy that has been absorbed in the form of visible light. Okay. So both this fluorescence and the phosphorescence, they happen in the visible light spectrum. Okay. So light is the emitted light, it is of higher wavelength. I've already told you this thing, that your lambda emission is greater than lambda excitation. Okay. So absorption and emission takes place in the order of 10 to the power minus 12 to 10 to the power 9 minus 9 seconds. So it happens pretty quickly. Okay. In phosphorescence, the delay in the emission in light is there, and the delay in period, it is fraction of a second. As I told you, it is greater than 10 to the power minus 4 second to few days. Okay. Now there is a terminology luminescence, which is basically a combination of fluorescence and the phosphorescence. Combinedly, they are regarded as luminescence, and it is called the process of. It is usually called the process of re-emission. Okay. Now, why this is happening? Okay. Now, why this phosphorescence or the fluorescence it is happening? It can be explained by the energy diagram, which is also regarded as Jablonski diagram. This Jablonski diagram, it is also sometimes regarded as pairing Jablonski diagram. Okay. Now in this case, what is happening? We say that there is a ground singlet state. There is a second electronic singlet state. There is a first electronic singlet state. Then there is an excited triplet state. Okay. So can any one of you can tell me what is the difference between a singlet state and a triplet state? Anyone? What is a singlet state and what is a triplet state?
Sir, in singlet state, the electrons have opposite spin, whereas in triplet state, they have same spin.
It is just the opposite. In singlet state, you have the electron spin which are opposite to each other. Because if you see in the ground level, you are having singlet state. That means singlet state, it is a low energy state. Okay. So if in a molecule, if you are having spins opposite to each other, so what is happening basically? The magnetic dipoles that are being created, they are getting cancelled out. So the energy is being cancelled out, and hence we can say that we are having this low energy state. Okay. When we talk about the triplet state, in the triplet state, the spin orientations, they are in the same direction. So there will be a net magnetization vector . Okay, there will be a net magnetization vector, and we all know that magnetic vector, it is not present alone, it is also present with an electrical vector or electric field. Okay, so in triplet state, the spin will be in the same direction, whereas in the singlet state, the spins are on the opposite direction. Good. Now, this ground singlet state, over here, you will have several vibrational levels, which I have not shown over here. Okay. To make the system more easier to understand. So let us consider that all the ground states, they are being accommodated within this H0 level. Now, over here, I have discussed that in the singlet state, we are atoms which are arranged or which are spinning in an anti-parallel fashion. That's good. So now, when you are exciting this electron with lambda excitation wavelength, then one of this electron, it is moving to the second electronic singlet state. But the rotation of the electrons, it is not being changed. Okay. The rotation of the electron, it is not being changed. Now over here also in S2 also there are various vibrational levels. Now this electron, it tries to move through the vibrational level, and it comes to the lowest most energy of the second electronic singlet state. And at this state, what it is finding? It is finding that it is having energy which is equivalent to first electronic singlet state, and it is moving over here. So the movement of this singlet electron from the singlet electronic singlet state to the first electronic state, it is called internal crossing. And when it is moving from S2 to S1, this is a non-radiative process. That means there is no emission of light. No, sorry. There is no emission of light. Now, getting my point? Now, once it comes to the first electronic signet state, so what is happening is that if you see, when we are having this lambda 2, so we are exciting it, this thing. So if you want to send one electron from S0 to S2, you have to use lambda 2 wavelength, right? Now, to this S1 level, you can send the electrons from the ground singlet state to the first electronic singlet state by incidentating another this thing wavelength excited another incident light or the excitation light having lambda ex of 1. So over here the lambda 1, it would be higher than the lambda 2. So in other way, you can say, as we move from left to right, there is an increase in the lambda, and since there is an increase in the lambda, there is a corresponding decrease in the energy levels. Okay, so now if you see, when the singlet electron from S2 it is coming to S1, there is an internal crossing, and during this internal crossing it is spending a non-radiative energy over there to come back to the S1 state, and hence there is a loss of the energy over here. Okay, now if you want to send the ground singlet electron to the first electronic singlet state, then directly, then you have to use a wavelength of lambda 1 to send that electron to the upper state. Okay, now this process, it is called absorption. Here also, when you are incidentating a lambda 2 wavelength, there is an absorption. There is an absorption process, and then there is a relaxation process, and this relaxation process, which is basically the internal crossing, it is a non-radiative one. Now from S0 to S1, when you have gone from here, you can come back to the ground state. There is a release of some light, which is again another relaxation process, and this relaxation process, it is the radiative relaxation process. Okay, and this process, it is called fluorescence. So lambda 1, it is going up, and it is again coming down to lambda 3, and it is coming at a higher wavelength. Now why it is so? Because within this S1 also you are having several vibrational levels, and while moving through the vibrational levels, there is a loss of some of the energies. And that's why you are getting the emission wavelength at a higher wavelength. Okay. Now, while coming to the phosphorescence, what is happening over here? There is an inter-system crossing. Okay, there is an inter-system crossing. Now, after doing the inter-system crossing, it is coming to the T1 excited triplet state. Now, herein what is happening? The electron in the ground singlet state and the electron in the excited triplet state, they will be having parallel spin. Okay, they will be having parallel spin, and when this electron it comes down over here, that process is called phosphorescence, and this is also a radiative relaxation process. Okay, now herein if you see the change in the wavelength when there is an re-emission, that is called that is due to the Stokes shift or Stokes law. Okay, that phenomena it is called Stokes shift or Stokes law. Okay, now there is another word. If you see over here, I have kept resonance fluorescence. So in the resonance fluorescence, what happens? We consider the case that there are no vibrational levels. And there are only S0, S2, S1 and T1, whatever I have shown. And this kind of thing are being are being exhibited by some atoms or rigid molecules. Okay. So is this clear? Why we are having fluorescence and why we are having phosphorescence, and what are the different relaxation processes, that is the radiative process and the non-radiative process. Is that clear to all of you? Now coming to the instrumentation of the fluorescence spectrometer. So we have the source, we have the monochromator, we can also have the filter. So in either of these two, what we have, we need to select any of the specific wavelengths, and then we will be exciting the sample with that source. However, in the absorption spectrophotometer, what we would have the detector assembly just in line with the source. However, in the case of fluorescence, this is not the case. It is at a right angle direction, 90°. Okay, this is because if you want to detect the spectrum in line with the source, you will also be getting the information about the source radiation. Okay, but we do not want that to happen. So we just want whatever the light is being emitted by the sample during the emission process. Hence, hence in fluorescence and the phosphorescence spectrometer, you will find that the detectors are at 90° angle. Over here also, once the light is collected, you can have the monochromator, and based on that you can detect the signal components and you can process it in the processor. So in fluorescence spectrography, you will find some peaks like this where you will be having wavelength and then intensity I at a specific excitation wavelength. Okay, so if you want to mm, uh, have the sample analyzed at three wavelengths, say lambda 1, lambda 2, lambda 3, so you will be getting three of such types of graphs. Okay, and another important thing, this fluorescence spectrography, it can help us in the understanding of the concentration of the compounds. Okay. Now coming to the light source, what are the different types of light source? We have low pressure mercury lamp. Then we can also use xenon arc lamp, which is a continuous source of radiation. Okay. So both of these sources provide a suitable spectrum of ultraviolet light that induces chemiluminescence. Okay. So chemiluminescence means there will be some chemical reactions which will give you some luminescence, and that can only happen in the ultraviolet region. Then the cuvette materials, if you are planning to work only in the visible region, then glass is sufficient. Glass cuvette is sufficient. However, if you want to work with the ultraviolet region also, then you need to use silica based cuvettes. Another important thing, I think whether I told you or not in the previous instance, when we are talking of the cuvettes, in the cuvettes from the top view you will be finding this thing. Okay. Now in the case of absorption spectroscopy, as in UV visible spectroscopy, suppose this is the light which is coming in I0, then you will be having the IT. So you will find the other two surfaces, this black, they are grounded, and hence they are opaque. However, this red marks, or I am planning or marking it in blue, these blue surfaces, they are the transparent surfaces. This is for the cuvette for UV visible spectrometer. But this spectrometer, this cuvette, it cannot be used with this spectrofluorimeter. Why? Can anyone tell me? Why you want to do this? Can anyone tell me why this cuvette cannot be used? This is because in spectrofluorimeter, we measure the emitted light at a 90-degree. So in this case, the cuvettes for the spectrofluorimeter, they are transparent on all four sides. Okay. So if you have a cuvette for spectrofluorimeter, you can use it in UV visible spectrophotometer. However, if you have cuvette for UV visible spectrophotometer, you cannot use it for fluorescence measurement. Am I clear to all of you?
Yes, sir.
Okay. Any questions? No. Okay, good. Now, with the advancements in the this solid state electronics technologies, the just like UV visible spectrophotometer, where we have double beam UV visible spectrophotometer, in in the fluorimeter also we have double beam spectrofluorimeters. Okay, so you have the source, then you have the monochromator, you have the sample in between, so it goes for so over here you may have a detector, Then another beam is being collected by beam attenuator and it goes to a reference photomultiplier. And over here also you have this excitation filter of the monochromator, and then you have the sample photomultiplier, and then both of this it goes to a difference amplifier, and then accordingly you get the output. Okay, so why we do this? We do this because when we are talking that we are collecting the emission spectra at right angle, it is also possible that some of the radiation source wavelength it comes in the 90-degree direction due to the phenomena of scattering, light scattering. Okay, so to negate that we need to have this we need to have this difference amplifier where we are basically negating the information about the source light through the emission spectra. Okay. Now coming to the molecular structure and herein we have to keep in mind that all substances they do not show fluorescence. Some of the substances they exhibit fluorescence under suitable conditions, and some may be converted to fluorogenic moiety. Okay, one of the classical example is the ELISA. Okay, where the counter antibody they are being tagged with some fluorescence moiety. Okay, then the molecules which has high absorbency they will most commonly show the fluorescence. Okay, then molecules or compounds that have multiple double bonds or conjugated bonds they can show fluorescence. Okay, then if you have one or more electron donating groups, then you can have the fluorescence, and these electron donating groups they if they are present in aromatic and heterocyclic compounds, then the chances of fluorescence it gets much higher. If you have electron withdrawing groups within your compounds like COOH, NO2, N double bond N, Cl, Bri, they will destroy the fluorescence. Okay. So presence, if you find these groups in any of the compounds, aromatic or the heterocyclic compounds, you can be pretty sure that it will not show the fluorescence activity. Okay. Then ring closure in aromatic compounds, they can enhance the fluorescence activity. The examples are fluorescein and eosine, which are highly fluorogenic compounds. Then polycyclic compounds like vitamin K, nucleosides, purine, and vitamin A, they have been found to have fluorescence activity. If some metals they form chelates, then they usually show this fluorescence activity. Also, the position of the chromophore over here, and if we change the pH of the composition, or if we change the solvent in which we have dissolved the compound, then there are chances that the fluorescence activity will be changed. Okay. So next is factors affecting the fluorescence. Concentration of the substance. If you take a highly concentrated solution, then it results in a phenomena which is called concentration quenching. Okay, so why that happens? It happens because there is a vibrational loss due to the intermolecular collision and reabsorption of the emitted fluorescence. Okay, so high concentration of the substance in a solution, they result in the concentration quenching, and usually this is we should keep the substance concentration in the solution to less than equal to 2%. So that means we need to use a dilute solution in the case of fluorescence measurement. Then presence of oxygen, it reduces fluorescence because the oxygen, it can induce oxidation of the fluorogenic material. Okay. Then photodecomposition, it may happen. Suppose you have a compound A and it is emitting some light. However, the light which is being emitted, it is causing the degradation of A, or it is inducing the degradation of A. So in that case also there will be a reduction in the fluorescence activity over a period of time. And again, if you use a concentrated substance, this phenomena will be much more pronounced. Then pH, in neutral and alkaline pH, phenol is weakly ionized. Phenol is ionized and it provides weak fluorescence. However, in strong acidic pHs, phenol shows strong fluorescence. Okay. Temperature and viscosity, increase in temperature and decrease in viscosity, it reduces fluorescence. Impurities like fluorescein and eosin, they can hamper your fluorescence measurement. Why? This is because, as I already told you, this fluorescein and the eosin, they are very potent fluorescing agent. Okay. Then coming to the chemical quenching, if molecular oxygen, iodide ions and acrylamide, they are present within the solution, they will be resulting in the chemical quenching. That means they can absorb some of the light and some of the emitted light, and you will not get proper fluorescence measurements. Okay. Then lastly, we have interfilter effect. Now this interfilter effect, it is being what you call, it is being observed because there is reabsorption of emitted light either by the solvent or by a quencher, which may be present within the solution itself. Quencher means just like this molecular oxygens and iodide ions and the acrylamides, which has the capability to absorb emitted light. Okay. Now the relationship between fluorescence and concentration. So there is an important number which is called fluorescence quantum yield, and it varies in the range of 0.1 to 1. So it is given by number of emitted photons divided by number of absorbed photons. Okay, so how these quantities they are being found out? So you have the sample holder over here. So you have I0, which is coming from source. In the line of the source, you will be able to get the number of absorbed photons, sorry, not protons, absorbed photons, and in the 90-degree angle, you will be getting the number of emitted photons. Okay, and fluorescence intensity, it is given by K multiplied by I0 psi, which is the fluorescence quantum yield, within bracket 1 minus 10 to the power minus epsilon Bc, where epsilon is the molar absorptivity of the analyte which is being under analysis. Okay. However, when we use dilute solution, as I told you, when we have this 2% of the only the 2% of the excitation energy is absorbed. Okay, in that case, this equation is being resolved into a much more simpler equation, which is given by k I0 multiplied by psi epsilon bc. Okay, in this case we have this fluorescence intensity. It is proportional to the concentration. Okay. Now coming to the phosphorescence spectrometer, in the phosphorescence spectrometer, it is also regarded as phosphorescope. Okay. So over here, what we have the light source. From source it comes. Just like the fluorescence detector, we do the measurement in at the 90-degree angle. However, there are two choppers which are used. So in the first case, the first chopper, chopper A, it allows the light to pass through it and it falls onto the sample. Okay. And at that time, the second chopper, the chopper B, it is closed. So there is no light from the chopper B to the detector. That means when we are exciting the sample, in between you will be having this monochromators and all these things. Okay, please be remembered. So when we are exciting the sample, the detector is made non-functional. Okay. Now in the second instance, we block the radiation from the source to the sample, and at that time the chopper B, it is being opened and the light from the samples, it goes to the detector and the spectrum is being measured. Okay, this type of arrangement, it is being done to ensure that no other light what you call um, light noises either from the source or the fluorescence activity, they are being recorded by the detector. Okay, so with this I complete this chapter. If you have any questions, I'll be happy to answer those. Do you guys have any questions?
No, sir.
So I will stop over here.